what am I going to say? Two things. First of all, last time we had an MDP. I'm not going to give the details, but that speed scaling example. I hate to say SS in this climate of today, but speed scaling, not SS in any 1930 sense. The thing is that what we ended up showing is that it's a sort of like I was joking faith-based math where you say if we could perform a Taylor series expansion and we got small error, then we could justify looking at differential equation. And when we solved the differential equation, we found out it was so smooth that our assumption was validated. We found out that this fluid value function and by the way, often I'll use that term fluid value function because that's often called a fluid model. You've got a discrete stochastic thing, and you look at sort of mean. It comes from queuing theory, where queues come in packets come in, packets drop out, and you approximate by a leaky bucket model where water flows in smoothly, and you can open up a valve at a desired rate. And because this is so smooth, our assumptions are validated, and you can show that with H equals J star, you can look at this Bellman error. Okay, so this guy doesn't solve the original average cost optimality equation, but I can look at the error. So this is a bit different. When I just defined the Bellman error, it was for discounted cost, and I'm talking about average cost. Okay, so what would this be if H was the actual solution of the ACOE?
Zero.
It wouldn't be zero because there's a constant. So you're right. If I had a beta there and I was looking at the discounted case, then it would be zero. But it's a constant. So the average cost case has that subtlety. So you would like this not to be zero, but a constant. All right. And we find that it is almost constant. It's nearly constant. And it goes, well, I'll say nearly constant. It's bounded, and it goes to zero. Which isn't maybe what you want, because I'd rather go to eta star. It's actually too good. It's sort of weird, So it's not quite right. Yeah.
How can it be nearly constant and go to zero?
Oh, I mean it's very flat looking if you graphed it. I think it would take a little jump at the origin and then be flat and go to zero. It's flat. It's. Yeah, you're right. That's yeah. The derivative is very flat except for the origin. There's always going to be something weird at the origin. The boundaries always do something crazy. But what you can do then is I can change things around a little bit. I can define a new cost function. So remember before I added b of x to define a new cost function? All right, I'll throw in a constant, and by the way, it might be negative. And actually, instead of positive, it might start at negative. I don't remember. I'll throw in a constant. What constant? Anything. I'll make it so that this is as small as possible, maybe. You know what I mean? I'll use it to center, maybe well, B better not be negative. That's why I think this is actually negative, not positive. I'll use it to move things around. But it doesn't matter. Okay, just a constant, 12. 12, we'll make 12. And if you plug this in, you know, I can take the B of x inside here, and there's a minus sign, and I can subtract eta from both sides. You know, and what you'll find out is that you solve the HGO, you solve the average cost optimality equation. Yep. Yeah, I did that on purpose. See, I mean, you see there's a minus sign here. So if I bring this over, I'll get a B plus C. So the B plus C is right. You know? Oh, yeah, excuse me. I just got lazy. Again, I'm always trying to save chalk. And you do get... Okay, so you know, so basically, with this fake function, it's not the solution. It's a solution to a different problem. It's a deterministic problem. But if I define this new cost function for any eta, I've solved the ACOE. You know, but of course, I'm going to try to choose eta so that this is as small as possible. So, yeah, I mean, you don't have to change your notes, but I have a feeling this is negative. And I'll choose eta somewhere in the middle to lift this thing up, you know, something like that, or something like that. Maybe I'll choose it to make sure this is positive valued. Because remember, I'm trying to take this to my CEO and say, look, I've solved the optimization problem, but with a different cost function. And it's a little bit different at the origin. It's a little flatter or a little bigger at the origin. You know, are you satisfied? And of course, you know, they're satisfied. So mission accomplished. The solution's solved. Nothing needed. It was a back-end envelope calculation. This was trivial to compute. And then you go through and you can compute this, okay? I mean, you know, you can estimate it really easily, and you see it's nothing.
X raised to 3 by 2, like that was specific to our example.
Yeah, the last time, the SS example, yeah. All right. And so for those of you who came in late, there were 2 questions about the exam. This was 1 question. Yeah, and this was like in the solution to the last termic problem. I made a big deal about this. This is called the asymptotic variance, which has a strange formula. And it's not the variance. The asymptotic variance is, in most physical models, it's much bigger because of positive correlation. My position now is positively correlated to my position a moment ago. And that positive correlation is what makes this often huge compared to the ordinary variance. Yeah. And so in fact, in the solutions, I gave an example where you had negative correlation. So my position a moment ago, you know, if I'm at 25, my position a moment ago was probably at minus 20. The negative correlation is when you get this thing being smaller than the variance, or maybe even 0. Yeah.
Quick question there.
Yeah.
In the homework, it says that the expectation itself without a t in front doesn't have the scaling factor.
No, it did. It did. You'll see. I hope there's not a typo there. If it's not a typo, then you all get an A. Yeah, because remember, this goes to 0.
No, that's fine. I'm saying like in here. Yeah, there's the asymptotic variance, but there's the steady state variance, which doesn't have the t in front.
Yeah, that's a variance. Yeah.
Yeah.
That's a variance. That's different. So the exam question is about the asymptotic variance.
The exam, you understand that's equal to sigma sub c.
Yeah, it's not. It's not.
It's not. The sigma sub c square will be the expectation, but without the t in front. That's what I'm saying.
No. Eta of t had a definite. Remember. No. So look back. You'll have to go look at the exam again. But eta of t was 1 over t some little t equals 0 to t minus 1 of c of x of little t. See, I mean, the variance of this monster could be huge. nothing like the variance of C. You know, the variance of this thing, I mean, really here we're multiplying by square root of t. So, you know, I mean, having a t outside, if I took it inside, I'd end up with the square root of t. Yeah. So the variance of this monster typically will be much larger than the variance of that little guy, one term. That was the point of the problem, yeah. Okay, don't worry, it was just a little bit. I'll give lots of partial credit. But again, I was said before, if you came in late, we're going to, when we get to reinforcement learning, all that, this is really going to be important. You know, it's you know, if you don't understand this, you won't know why your algorithms don't work. You know, so we'll come back to this. All right.
The computer science people don't.
And the computer science people don't. I mean, I think largely they don't understand that.
The exam,
Yeah.
just
Yeah.
on the last question, the true and false, the one where you were essentially, you had the function g, which is just
Oh yeah.
equal to c tilde.
Yeah.
Because you're shifting the mean down, then that would be true, right?
Well, the question was, if you have g equals dh,
Yeah.
does that imply that pi of g equals 0? And, well, for a finite state space Markov chain, you know, the state space is finite, yes.
Yeah, I think that's what the question said.
Yeah, so x is finite. Yeah. Okay, so in the homework, I had an example where h was 0 to the minus x, and this wasn't true. But that's because it was an MM1Q, it was an infinite state space, so things can go wrong in infinite state spaces. But for a finite state space, dh, you know, g is of the form dh, pi of g is 0. So, right? Yeah.
Yeah, pi of g converges to eta.
No convergence. There's no convergence here. This is all just multiplying matrices together. Pi is a row vector. Pi d equals 0. It's nothing but convergence. Nothing about anything.
No, but even in our general case, like eta is 0 in this case, right?
Well, yeah, but I mean, sure, but I'm not sure that's helpful. Yeah, and the pi dot g is 0. Let's just, you know, yeah, you know what I mean, because there's no eta. G is not a cost function, you know. Yeah, I mean, here we had c of x of t, and it was a cost function. Eta is its mean, and yeah. All right. Yeah. Okay.
I had a question. I guess maybe it's not so relevant right now because we haven't gotten to that yet.
Yeah.
But I was wondering, because you had said that a lot of people in that community don't necessarily understand why it is that their stuff doesn't work.
Yeah.
What is it about the size of eta? I guess you're saying it's going to be larger or something. But what is it about that? What is it that not understanding what that means will cause your algorithm?
Yeah, well, the thing is that because many people in the field don't even recognize that their algorithms fit inside of a broader statistical framework. So it turns out that Q-learning, reinforcement learning are just special cases of stochastic approximation. We'll get to that later. Because they don't even recognize that. They don't read that literature. And so when it doesn't work, they say, shit, it doesn't work, and they come up with reasons. But if they understood the literature, they'd go back and say, oh my God, my gain's not right. And so what we're going to learn is how to, that homework problem I gave you with a little g, you know, you're going to learn why I gave you that. G equals 1 is optimal, it turns out. And this theory explains that. And the same theory tells you how to optimize Q learning and TD learning. Yeah. So that's, you know, that's
Is the idea of it kind of on like a bar scale of maybe estimating this thing, is it saying that, you know, maybe at the beginning, because your error is so large, that it's not a good idea to really trust what you're doing?
Well, it's also, you can maybe improve your algorithm if you think about it harder. That's, you know, so partly yes. I mean, if this is huge, if that's an enormous number, then you need to, the t has to be much bigger than that number for decent results. But also, you know, how do you make it go faster? Yeah. And yeah. And also, sometimes you think you're doing really well, and you're not. And I'll get to that as well. I mean, some of you, I think, said that a gain of a half in that homework problem was great, and it's because you were seeing this. Your estimates were constant. And you think, all right, well, anyone can draw a straight line. You know, I could say my estimate's 0 all the time, and wow, look at that, perfect, it's flat. You know, so it's knowing whether you have a good estimate or not requires some science, and we'll get into that a bit. Okay. So, but yeah, and there's Matthew Silic. Who's Matthew? You're Matthew. Okay, we're looking for you. Is that Serbian, by the way? I mean, okay, Croatian then. Croatian? Oh no. Okay. Around there. Okay. Sorry, I didn't mean to put you on the spot. All right. So.
So if E is positive, it's okay for eta to be negative?
Well, in this case, it sure would be stupid because I had a positive cost function, so it would sure make my COO suspicious if I found I got a great solution. The average cost is negative, so so actually you probably should make eta set it up so the new cost function you're taking to your CEO. Oh, sorry. So your new cost function is not negative valued. Otherwise, it would look suspicious. So eta, yeah. Okay. So I don't know, I think it was last week I said there's 3 algorithms we'll look at. Those are the 3 exact algorithms. So if you have a finite state space Markov chain, controlled Markov chain, you can apply value iteration, policy iteration, or linear programming. I sent you guys notes, lecture notes for goes through and explains, what this is. For the algorithm, you can just go and type in Wikipedia policy iteration.
V/A?
No, VIA. So and it's in these notes. Value iteration algorithm, and it's all right here, and policy iteration. So we'll knock these off today. I want to give you some intuition. And mainly, anyone can go and look up the algorithms on Wikipedia. I mean, it's trivial. I could just send you all off to read it and do the homework. So like to do this last homework assignment, which I just posted, and it's just due next Thursday, because you've got it, it's before spring break. So, and I want you to get your hands dirty with an assignment. You don't need this lecture. You don't need this course to do that problem. You can just go to Wikipedia, type in value iteration, get the code and do it. You don't need anything. But I want you to see where these things come from. And because if you understand where they come from, when you come up with some different context, you can cook up your own algorithms. So basically, what do we have? Okay, I'm going to do this all in the context of the average cost optimality equation. That's almost never done. So in courses, they look at discounted cost. And that's one advantage. You only get it here. People typically say the average cost is similar. I'm going to say, well, the discounted cost is similar. Yeah.
About to work off the latest course handout.
Yeah, I broadcasted these just now. Yeah. Yeah. You don't need to take notes. Everything's in these notes. So, but it keeps me awake. I take notes anyway because I stay awake. So we've got the average cost optimality equation. And as I said before, it's not, the solution's not unique. So there's two unknowns here. We don't know eta star and we don't know 8 star. Eta star is the average, optimal average cost. 8 star is this function we're trying to find. So one thing we can do is we can normalize 8 star. So remember we have that x dot that I'm always using that, and by the way, x dot, x star, I keep on using them back and forth in these notes, sorry, but stars and dots are the same with those x's. We're always taking this distinguished state that we've been using. Let's normalize it so that's just h of x dot, you know. In the notes, I put a star there. That's a typo, but to hell with it. The stars and dots are the same. Sorry, you know. You can do that. You know, I don't know eta star, so I don't know how to normalize this, but I don't know anything. So just assume it's true. So now the solution's unique. You know, or at least I don't know that. We haven't proved theory. It could be there's a whole 10-dimensional subspace of solutions or something. That's actually not true. Under general conditions, the solution here is unique up to an additive constant. You know, and I'm just specifying by doing that I've made it unique. Yeah. No, it's just just like before. It's all the Markov chain theory. We just pick some state, and we just whatever. It's arbitrary, really. It doesn't mean anything to optimality. It's just we just take some arbitrary state. It would be something. We will assume that pi of x dot is positive if pi is invariant for the optimal policy. You know. So in the end, when we find the optimal policy, we apply that, we get a Markov chain, you know, that achieves this optimal average cost. And in order for the theory to work, you have to actually have that to be true. That requires some knowledge of the problem, but
Can you break that statement there below it like is like pi p sub u star and equals pi in the sense that like.
Well, yeah. Well, very often I will use that notation. Pi phi star of x is greater than 0. That's true.
I meant more like, so you're saying it's a very optimal policy of like p sub u, like if we substitute.
Yeah.
That's where that.
All right. You're making me do it. I was about to do this.
I'm kind of asking like the pieces of how the policy affects it. Should be kind of imagine effects on the piece of you.
Okay, so I mentioned before that I'm going to define policies by a function from states to action, states to inputs. And if we do choose a state feedback, okay, so notation, first of all, my policies, a stationary policy it's called, but really we'll restrict to that usually, is a mapping from states to action, states to inputs. And if I apply u of t equals phi of x of t, it's really easy to see that the resulting stochastic process is a Markov chain, because you can write down as transition matrix, what's p phi? So for any pair of states x and x prime, well, I did something weird. It's an abuse of notation. We do that all the time. I'm just replacing u by phi of x. you know, you're so used to abusing notation you don't even realize it. But in math, you just often don't want to have to keep writing that all the time. And so you just suppress the of x. And you have that. And it's really nice to say, under state feedback, I've got the resulting stochastic process, a Markov chain with transition matrix P sub phi. Right? And so what I mean by this is that pi phi star, p phi star equals pi phi star. Yes, and I thank you, because we really do need that notation. Okay. Yeah. Is that clear? All right. All right. So by doing this, now I can go and get rid of that and replace it by h star of x dot. And again, the notes you'll see x star, but that does look like it's saying optimal, and that's sort of weird. I mean, it's not. It's arbitrary. It's not optimal. And you know, in most cases, we have irreducibility. So this is positive for every state. You know? Yep.
What precisely are you normalizing?
I'm just saying H is not unique. So the solution to Poisson's equation was not unique. We could always add a constant and get a new solution. The same thing is true here. You know, I can add a constant. I can add one, you know, add a single constant to both sides of this equation. I'll get h star of x plus 1, say, for every x. And I can take the 1 inside, because that's a transition matrix, and I'll have h star plus 1. You know, I can add a constant to either side. As soon as I fix it and I say no, I'm going to make it unique by making sure that at that point it's equal to eta star. Then suddenly I get something where there's only one unknown. Instead of having two unknowns, h star and eta star, I have one unknown and uniqueness, and that's important for algorithms. You know, I don't want lack of uniqueness. I want to say there's one solution. We're going to find it. All right. So how do you find it? We need to put this in a context of you know, how do people solve fixed point equations? And they do it by playing around. I want to put this in the context of where, you know, you might have seen Newton-Raphson somewhere. Yeah, yeah. All right. Yeah, well, you know it's an algorithm. So let's put this in the context of Newton-Raphson or whatever. So to do that, I'm going to define a function on functions. So please, just let's, for the rest of the, you know, the next lecture is finite state space Markov chains, okay? Let's just, so H is a function on a finite state space, real valued, so it can be thought of as really a d-dimensional vector, okay? H of x1, H of x2, H of x3, up to H of xd. And I'm going to define for this, I'm defining something which takes a function and gives you a new function. So I could put of x like I always do, but it's just so confusing. I'm going to put that other notation. All right. So given a function h, I define a new function of x. So this is a new function of x. I'm evaluating it at x, and it's given by that. Okay, so what have I done? I've taken this h of x dot and I've put it on the left-hand side. And so my ACOE becomes a fixed point equation. Okay. All right? The ACOE says 8 star of x equals this minimum plus, minus 8 star of x dot. See, it's all right, it's written there, you know? So I'm just rewriting this equation in this form. You know, and you can see if you want to save chalk, I did a great job. But the main thing is that, so I know of 2 ways to solve a fixed point equation. Does anybody know what they are? I mentioned one of them. What, Newton-Raphson's one? That's the hard one. What's the simplest trivial thing everyone always does?
Guess and check.
What? Guess and check. Yeah, guess and check. I guess that is guess and check. Yep. That's right. Solve a fluid model equation and plug it in. Yeah. Yeah. Successive approximation. Yeah. Yeah. All right. Yeah. Yeah. So that's a beautiful fact, you know. And, you know, I didn't know, I knew about policy iteration forever and ever and ever. I don't remember when somebody told me it was Newton-Raphson, or I figured it out myself or something, I don't know. But it's pretty crazy. But you will find it way back in the books. I mean, in 1970s book of Bitsicus and Shreve, it's explained for discounted costs. It's Newton-Raphson. It's, you know, Bellman did everything. I think it was probably, he probably figured this out once, maybe didn't tell us. But but this, you can imagine, is really crazy because Newton-Raphson is about linearizing a fixed point equation. So, you know, when we had Poisson's equation, it was just like this without a min. It was a linear equation. I've explained to you how you can convert it to an inverse problem. If you go back to your notes, you'll see that. Now I've got a nonlinear equation, and I've got to linearize this thing and solve it. What the hell do we mean by that? So this is sort of fun and hard. This is so trivial, it's absurd. We won't bother. I'll tell you what it is, and then we'll move on. Okay? Yeah. All right, shall we? Well, actually, no, don't say that. Erase that. Successive approximation. So first of all, you have to initialize. You have some, you know, you have some intuition, and you think, well, yeah, the guess, whatever it was. You have some guess you think is, you know, like your, like my fluid value function, and you take that as a guess. Okay, so that's the definition of successive approximation. You know, the new guy is just t of the old guy, and you just do it over and over and over again. You code this up in 10 seconds, and that's the reason why this is the favorite algorithm, because it's just so trivial to come up with. But now, when we unravel what this means, it's going to look familiar. All right, so,
This only works or applies for a finite state space?
Well, no, actually, the thing is that you can only run this if it's a finite state space. But in terms of analysis, like there's a lot of theory about trying to get structure of policies. Like that square root form I had for the speed scaling model, or threshold type policies. A lot of times you want to prove that a value function is convex or something, or because then you can deduce some structure of the policy. So even for infinite state spaces, you can use inductive proofs to say that if Hn has some sort of convexity property, then so does Hn plus 1. So there's all sorts of examples of that. So it's an analytical tool. It's used all the time, even for non-finite state spaces, but for computation, of course. Yeah. Which is weird again, because I mean, if you're a continuous space person, nothing's ever finite. Calculus is beautiful, you know. You end up with PDEs, you know. So it's strange that we're saddled with having to deal with only finite state spaces, but people who work in continuous spaces have PDEs. Yeah, it's a weird disconnect, you know. Anyway, finite state spaces. All right, so let's plug this in. It's a bit weird. We just plug this in. It says that Hn plus 1 of x equals T of Hn evaluated at x, which is this. All right. Now, there it is. Algorithm. You can run this and go for it. All right. It'll be pretty slow to run. It might take thousands of iterations to get a decent fit, but it's so fast to code that it's worth it. It's so trivial. Now, this is not what they do, though, because why would I bother keeping track of this constant? You know, I can always throw it back in later. I mean, just, you know, to hell with it. Who cares about constants? You know, when I solved this, it was really arbitrary to make this equal to eta star. Just toss it away. So real value iteration in the text forget constants and just let this thing run. All right, that's the definition of value iteration in this context. And that looks familiar, right? That's exactly, without the minimization. Remember, that was the way the lousy approach to solving Poisson's equation that I mentioned before. Yeah.
So does this give you an actual function back, or is this just give you the specific value?
No, for each x. Oh yeah, each x. I mean,
so you have to run it in each x?
No, remember it's a finite state space. Yeah, so I go through and I go for x equals 1 to d, you know, perform this minimization. What's that?
Each n we can imagine is a vector that we're solving.
Yeah, that's right. Yeah. This is a mapping.
For each x.
You take this minimum. Well, in MATLAB you can do it all in vectorized form, and I definitely recommend you do that. You can do that.
Because PU can couple the values together when you do PU times H.
Yeah.
All of the values are like coupled.
I'm curious. I hope some of you are really good at MATLAB. I want to see what you do, because you know, if you code this well, this can fly. If you do a lot of for loops, it's horrible. So if you can avoid for, if you can do your code with no for loops.
What's make a call to the value iteration?
No. Right. No. You can do everything. MATLAB is designed for vectorized problems. You can minimize a vector. You can.
X0 or X dot.
What's that? Oh, no. Remember, I didn't do it. I didn't bother.
Oh,
yeah.
So when we're doing the thing, we just ignore that?
So this is a definition of successive approximation. All right. Okay. In value iteration, you just say, oh, screw constants. I don't care about them anyway. You know, I only did this so I could define this operator. You know, and so I could you know, define successive approximation and Newton-Raphson. That's my only motivation is analysis.
If you run the bottom one,
it'll blow
what's
up.
going to happen?
But But if they're both initialized in the same way, the thing is that you throw away the constants, you can put them back in later, you know. And so basically, this is just a number, you know. It's just a number, and so I can basically take these numbers. I could, find them here and then add them all back in. But this is just a very compact way of saying that they only differ by a constant for each x. All right? Yeah.
So in this algorithm, do you assume a polynomial or something for h and like find?
No, finite state space. Finite state space. Yeah. So we'll get to approximation methods later in the course. But here, the finite state space for each x, you perform a minimization.
So like, how are we getting the function h?
Oh, this is minimization. So given hn, it's induction.
So do we assume a function for h?
No, h. Remember, it's just remember. We've got h0 is just h0, of x for x equals x1, x2, up to xd. Just think of x as an index again. This is just a d-dimensional vector. So I take a d-dimensional vector, in this case, vn, and it gets mapped to a d-dimensional vector vn plus 1, because you perform this for each x.
So you're getting individual samples of H.
Samples.
Not like
Samples. No, the finite state space.
This is the crux of the question.
Yeah.
Is that you're not getting an expression for H in terms of these finite x's. You're getting
Oh yeah.
individual values.
I could store this in memory.
But you're not getting like
H is a function over a finite domain. You're going to get a list of H's values.
Yeah.
Right, but you're not going to get H of 1
Yeah.
equals 1 squared, H of 2 equals 2 squared.
We'll do whatever. Yeah, this could be 2 squared. I mean.
Well, but you're not going to get that expression x squared. You'll get 1, 4, 9.
I understand.
That means H when the state is 2 equals this value.
Yeah.
Like I could plot this H vector.
Right. But I think the question is that you're not going to get an expression in terms of an analytical expression in terms of x. You'll get individual.
Yeah, you'll get a table. Yeah.
So,
Yeah. That's right. Yeah. I'm just like any algorithm. I mean, yeah.
so you will run this thing until the difference between Bn plus 1 and Bn
Yeah.
falls below some.
You might look at that Bellman error, and when the Bellman error gets small enough that it would please your CEO, you stop.
Okay.
That's
But that's the fact that we're ignoring the constant here coming.
It doesn't matter anyway. Constants are irrelevant.
Because they're always going to get taken
You
off.
could always throw them away.
There. Okay,
Yeah.
I see. So when you're taking the difference, the constant doesn't matter.
Constants don't matter, yeah. So I'll run this until the Bellman error is small. And Vn is some huge thing, so I will actually take that as my solution. It doesn't have, it has a property that this difference has a property that the difference at x dot is 0 instead of eta star, big deal. Constants don't matter, Yeah. So
like I know what PU means in terms of like the expected value definition, but like in practice, like what are we going to have a matrix that has constants and u's in it or something?
yeah, you're gonna have that Homer problem will help. That's why I want you to just do it right away. So you'll have to do this matrix vector multiplication. And so this, and again, you visualize this as a matrix with a lot of rows and only d columns, because the rows are both in u and x, You know what I mean?
But
Yeah.
it's like, so our choice u, that's also finite?
Yeah, it'll be finite too.
Finite.
Yeah, finite input space as well. So in the Homer problem I gave you, there are only 2 actions: drive the little robot or don't. And then there were 3 states: top of a hill, bottom of a hill, or in the middle.
Okay, so So it's kind of like the rows are going to be, if you're starting at this x and you use this u.
Yeah.
So we're going to get, like, if the state space has
Yeah.
n states and we have m inputs, it's n times m by n.
That's right.
Okay.
It's a huge monster of data. Yeah. Yeah.
And you're going to give us, like I mean, not you're going to give us in practice,
Yeah.
we're going to just somehow know these probabilities.
Yeah, maybe you'll do some experiments to estimate them, you know, and yeah, and then there's
So that's your model.
and that's your model, you know, yeah,
Transition probabilities of your dynamics.
yeah, that's right, and yeah, like in that speed scaling model, you know, you had estimates of the arrival statistics and
I
the
kind of want to see, like, if we had like the MM1Q example,
Yeah.
how we would go from that equation, not assuming U was
Yeah.
the policy that we always assume.
Oh, it's easy.
Build the PU matrix. Like,
Oh, it's easy though.
it probably is. I just need to like work it out.
Oh, no, we have done it actually.
We've made the PU matrix from that.
Yeah. Oh yeah. I'm just gonna write this down and have you think about it.
Probably just write the result.
There's the whole table. So remember, so phi, so again, u of t equals phi of x of t. And the only actions are work or don't work. So u of t can only be 1 or 0. You know? And so, yeah, so the probability going up is always alpha. I can't control the arrivals. But the probability going down is mu only if phi of x is 1. Otherwise it's, so I could have written minus phi of x. It's a more compact way of saying it. But anyway, there's the table. Yeah.
Okay, so here we have a not finite but countable
Yeah.
state space.
Yeah.
So we more like treat this, like I obviously couldn't write this as a matrix. Instead it's like a
Yeah.
lookup you call to those functions and you get back that because the
Yeah.
matrix has a lot of repeated values.
You couldn't run this though. You have to truncate the state space. And if you do, it's really awful what happens. It's just, it's not easy. It's hard to explain, but if I took the MM1Q and I said, well, hell, it's unlikely for there to be more than 100 customers, when you apply this algorithm, you don't get the optimal policy. You know what happens? When the Q starts to get high, you say, fuck it, let's let it overflow and let them fall away. So you end up with phi of x being 0 for large x. It's really awful. Yeah, and yeah. Because there's no cost of just kicking people out of the system. Yeah, Comcast.
For service method.
Exactly. Like, oh, that's right. Yeah, it is optimal. It is true. It actually is some rationality.
We could, with just those rules, run this for the actually like infinite countable.
Well, no, we couldn't because we'd have to say for x equals 0 to infinity. You know, so it run out of memory, right? And there's no, yeah. You have to store this entire vector.
Yeah.
And so if it's infinite dimensional, you're screwed. Yeah.
Okay, so basically, as we have written it, this only works for finite.
Yeah.
Okay.
That's right. And we'll have to use we'll use approximation methods for infinite. Yep.
Maybe I understood, but so this PU of x prime for each iteration, is that a row? Is a single, for one x prime, PU of x prime a row?
Well, no, yeah. I mean,
For a U,
That's
right? For
an
a given
individual
U.
value for some given.
Yeah.
well, for each u and x, there's a probability mass function which we interpret as a row vector. That's true.
And then the h of x prime,
Think of that as a column. I mean, think of h as a column vector. Yeah.
x prime is going to be my entire state.
Yeah, I'm summing over all x primes.
So there's a three-dimensional array there?
Yeah, I mean, you can either think of it as is a very high matrix. I mean, very high matrix. A very,
Yeah, you have your,
Yeah.
I took
decision
you take the
between-
depth and you bring it down.
and the
Yeah.
dimension will be your
Yeah. You could think of it that way for sure. It's easy. Yeah, that's easiest for me to think of it as a parameters family of square matrices.
These are permutations of U and X.
Uh,
Rows.
So this,
permutations? I mean, no.
Like, for each X you have,
Well, each x I'm just summing over all x primes.
for the P matrix, for each X you'll have a U as well.
Yeah, I mean, for each x in U, I have a probability mass function. That's right. You know, and yeah, and and so I've got a whole, So for a given x, I take the minimum over U. You know, all those probability mass functions. Yeah. So it does help to code this yourselves. Yeah. Yep.
just so I'm trying to make it concrete in my head.
Yeah.
So for this one here, let's say that our space is 1 to 10, then
Yeah.
would X prime, then we just say, let's say we're starting at,
Yeah. We'd sum from 1 to 10.
so H of X prime, 'cause from what I understood before, you were saying that we could go at this as H is some operator on
No.
some R D vector, right?
No, H is just a function on these D elements, and D might be 10, as you say, and X1 is just 1, X2 is 2.
You initialize it, you would just say random, H equals random 1 or 10.
Well, that's a different question, though. I mean, first, we'll get back to that. Think about it yourself for a second, initialization, because I mentioned that yesterday, in our last lecture, but H, we have a vector because, we have a H of X1, H of X2, up to H of X10 in your case.
So I guess what my confusion is how can, if H is, we have this finite state space, we only have 10 state or 10 spots that are possible.
Yeah.
How can X prime be more than one thing?
No, it's not. We're just summing over. If you say the states are 1, 2, 3, up to 10, I will sum from 1 to 10.
So then it's going to be
It's just-
some row times. So PU of X prime is going to be 1 by 10. For each.
For an individual X prime.
For individual U and individual X, I have a row vector of dimension 10.
And so PU of X prime is going to be a 1 by 10, and the H of X prime is just a one element thing.
H is a vector.
Single X prime, P, U, X prime is a scalar, and H of X prime. And if you can imagine that sum as then making it a row vector times a column vector.
Right.
Yeah.
Okay. So, yeah, that's what I was thinking originally it said, but then I got confused by the
Yeah.
fact that we were saying H was a...
But it's almost no different than before, though. And without the U, this is just matrix vector multiplication. But now I've got a parameterized family of matrices. Yeah, and that's why I have to minimize here over U.
So you're concatenating the third dimension?
Yes.
Yeah, there's lots of ways to build this up.
Pairs of states and inputs, so we're taking all possible pairs and turning that into like the whole
Yeah.
row dimensionality.
And making it into a cube probably does make sense in terms of coding, I think. That's probably, I'll bet you're right that that's the best way to code it up. I have to think about that. But some of you are probably better at MATLAB than I am. So, yeah. But so somebody tell me what, like for the speed scaling example, if I truncate the state space, what's the initialization? 1, 2, 3.
I got an example. Hold on. I was looking at the
Beginning of lecture. Beginning of lecture.
H of X equals 0. That's what I would do.
It's right here.
Okay. We'll have a short break, and when we're done, I got to pick on one of you, and you'll tell me how you'd initialize it.